Hello student, with the next class of web optics. Today we will going to have lecture number 8 and we will going to discuss more about the nature of the superposition of wave, and when the two waves are randomly interfere, then what should be the form, and if two waves are not randomly interface, they have a synchronization, then what should we get at the output. Okay. So we should have today lecture number 8, and we were discussing superposition of waves. So in the earlier class we find that if we have waves like E1, E2, En in complex notation, where Ej is Ej tilde, rather Ej0 e to the power of I alpha j, and if I add all these things, so Er, which is the resultant wave, having the form E0 e to the power of I E0 e to the power of I alpha, then Er tilde is sum over j from 1 to n Ej tilde, and if we want to find out E naught from here with this, then E naught square essentially sum over E j 0, j goes to 1 to n, square of this quantity plus 2 of sum of j greater than I, sum of I, that goes to 1 to n, then E j0 E I0, and then we have cos of alpha j minus alpha I. That is the resultant amplitude one can have if I add these waves. Now after having that, we will going to describe two cases: random and coherent, very important term, source. Physically, what is the meaning of random and coherent source? In random source, what happened that the wave that is coming out from a source, suppose this is the source S, the wave that is coming out from this source so I mean for different source, rather I should not say but single source, all this for individual source, all cases we have individual sources. Okay, let me draw it properly. So in all cases we have individual sources. These are n number of source point which is emitting light or emitting wave. These waves are randomly phased. That is, at a given time, there is no phase relationship between these waves. We have n number of, so we can have for n randomly phased sources randomly phased sources with equal amplitude. Let us consider the amplitude to be equal for the simplicity. And frequency. What happened that we have n number of sources where their phase are randomly oriented, and we also considered their frequency and their amplitudes are same. In that case, what happened that the average value of this quantity cos alpha j minus alpha I should be 0, because this value will vary from -1 to 1, and since their phase relationship is random, then the argument of the cos value will change in a random manner. And if we try to find out what is the average value of this quantity, obviously for large n this is happening, not for small number of n, 1 or 2 or 3 or 5, say thousands of n if I do, and then if I add the cos alpha j minus I term, then what essentially we get that this value will vary from -1 to +1, that is the cos value, that should vary from -1 to +1, and if I average that quantity, then essentially we will going to get 0. So if that is the case, that if randomly oriented source and source are there emitting waves, and if I add all the waves, so the value of E0 square will simply be sum of E j0 square, where j goes to 1 to n. Now if all the amplitudes are same, then I am going to get n multiplied by that amplitude, we say EA. So EA is the amplitude for all the waves, same amplitude, whatever the, so J10 equal to J20 equal to J30 is equal to EA. So the amplitude will be multiplied by n factor if we have that the source that we are having here are randomly phased. Now what happened, next thing is, if okay, before that I like to mention what happened in the intensity, because that is the quantity normally we look for. So intensity I, that is proportional to E square, and we get E is equal to N multiplied by the individual amplitude, say EA, which is same for all the waves. So in case of light, when the intensity is proportional to the amplitude square, the irradiance, I is intensity or irradiance, of n randomly phased source is equal to simply sum of the n individual irradiance. So that means if we want to find out the irradiance for all the summation of all the waves randomly oriented, then that is simply n times of individual amplitude or individual irradiance. So the irradiance will simply add up here. There will be all the individual irradiance will simply add up if we have n number of sources, they are not in phase. However, another case we can consider, let us put case number 2, where we have n coherent sources. So for n coherent sources, which are in phase, such that alpha I is same for all the waves. So essentially alpha is equal to alpha j. In that case, so I have in, so let me draw the figure. There are n number of sources, and these sources are emitting waves in form of light, say, with same phase. Their phase are same. N sources with coherent phase, incoherent sources. So they are in phase. All are in same phase. So all are in same phase. In that case, what happened, if I add all the waves, if all the waves are add up, then the value of the resultant amplitude square, E0 square, is E J0 j goes to 1 to n, that is the first term. And second term, since all the alpha are same, so we can have cos of alpha j minus alpha I. This will be 1 as alpha j is equal to alpha I. So we have 2 of j greater than I goes to 1 to n, and then we have e j0 and e I0. Okay, so this quantity, if we look very carefully, this quantity is nothing but sum over j going to 1 to n e j0 whole square of that. So it is nothing but, if I write this, a1 plus a2 plus a3 square of that is essentially a1 square plus a2 square plus a3 square plus 2 of a1 a2 plus a2 a3 plus a3 a1. That's all. This restriction j greater than I and I goes to 1 to n will give us these combinations. So if now all ej's are same, so ej0 we mention that it is ea, all the values are same for same amplitude, then my e0 square is essentially sum over n, not sum over n, it is sum over, okay, let me write down once again, j goes to 1 to n and it is e j0 whole square, and that value is n multiplied by ea and whole square of that. That is a big difference between the previous expression where we get this e is equal to n of e. Now here we had an expression that okay, in the previous case what we get e0 square we get n into a, so it is e square that we get, and here we get e0 square is equal to n square into ea square into ea square. So obviously this value e0 square equal to n into ea this is n into ea square. I make a small mistake here in writing in the previous case, and here it is n into ea square, but this case this is e0 and this case it is e0 into is equal to n square into Ea square. So once n square is there, if the number of n is too large, then there is a huge difference between the two amplitude of the two sources. In one case we have n multiplied by, so if I write this case for okay, let me do it here only. Then what is the meaning of that? The meaning is irradiance or irradiance of in coherent source in coherent sources is equal to n square multiplied by irradiance radiance of single source. So irradiance of incoherent source is equivalent to n square multiplied by the irradiance of the single source. Previously we find irradiance of the n randomly phased source is equal to sum of n individual irradiance, but here n individual one individual source amplitude will be multiplied by n square if the sources are coherent. So obviously for coherent source we have much higher value of irradiance. Okay, let me go forward to the next concept regarding the superposition of waves, and that is called the standing wave. As the name suggests, here the wave does not move. So superposition of the two harmonic waves of the same frequency propagate in the opposite direction. So same frequency superposition of the two harmonic wave means one wave is moving this direction and another wave is moving this direction. So if I add these two, one is forward propagating and another is backward propagating, if I add these two with the same frequency, then they will going to form a standing wave. Suppose this is E1, which is E0 harmonic wave, so I can write sine kx minus omega t, which is this direction, and another wave which is moving in the opposite direction, so it should be E2 is equal to E0 say sine and then kx plus omega t, because it is moving in other direction, so that's why if it is plus, if it is minus, then it has to be plus. With a phase, let me add an additional phase, maybe whatever the wave that is moving in the opposite direction is having an additional phase, and we write this phi r, which is the relative phase. So phi r is the relative phase between these two waves. Phase. So if we put these two together, then the resultant wave as a superposition of principal, using superposition of principal, we simply have E1 plus E2, and this is amplitude is same, so it should be E0. I write sine, say I write this is term beta 1, so I write this is beta 1, so this is my beta 1 and this entire thing is my beta 2. So this quantity I write beta 1 and this quantity I write beta 2. So it should be sine beta 1 plus sine beta 2. So okay, let me write it here. Beta 1 is equal to kx minus omega t, and beta 2 is kx plus omega t plus phi r. So this quantity is 2E0 sine of beta 1 plus beta 2 whole divided by 2 and cos of beta 1 minus beta 2 whole divided by 2. And essentially what we get is 2E0 sine of beta 1 plus beta 2. If I add these two and make it divided by 2, it should be simply kx plus phi r divided by 2, and it is, sorry, it should be sine term here, sine of these things and cos of kx, not kx, because when we make a negative it should be omega t, cos of omega t minus phi r by 2. So essentially what we find that the resultant equation, so this is not in the form, if we look carefully, not in the form f of x plus minus vt. So the resultant wave, even though we start with two propagating waves, but when they are superimposed with each other, I can separate out the x coordinate and t coordinate, the space coordinate and time coordinate individually, and it is not in the form of x plus minus vt. If it is not in the form of x plus minus vt, this is essentially not a wave that is propagating. So whatever the resultant wave we have, these are called the standing wave. They are standing in the same place. So if, let us take phi r by 2 is some quantity, let us put some phase like pi by 2, then er will be simply 2 of E0, then sine kx and cos of omega t. So so let me check if I, so sine a, so this is sine a, sine a plus b, it's sine a cos b, and then cos a sine b. Okay, so okay, so if it is okay, so make it simple. So this quantity 5 by 2, I so it should be cos and it should be sine. So in order to make this, let us make life more simple actually. So let us take this is 0. So there is the relative phase between these two zeros, the most simple case. Then maybe we go to other case. then we simply have this in my hand, that ER is two these things, sine of this and cos of this. So this quantity is the amplitude, and if we fixed a point x equal to x0 and look what is happening for this wave, we can see that this wave will going to change over time and with a frequency. So let me draw it, what is happening here, try to understand that. So this is, say, was the forward propagating wave, and because of the backward propagating wave we have a standing wave, and we get something like this. So this is my E2 and other one is E1, and they are superimposing to form a wave. They are superimposing and form a wave, a resultant wave actually, which is standing and which is changing over the time. Its amplitude, maybe I will draw like this. So its amplitude at some point is changing from maximum value to minimum value. Sometimes it goes to 0, sometimes it goes to over the time actually. So it vibrate like this. This is the point which we call the nodes, the node. So the form is ER, the resultant waveform is ER is equal to 2E0 sine of kx multiplied by cos of omega t. So as I mentioned, at fixed place, for example here, this is some point at x equal to 0, this wave will going to change, the amplitude of the wave will going to change with this form, 2e multiplied by cos of omega t. So over the time this value will vibrate and we will going to get 2 value 2e0 and minus of 2 0, it will vibrate in these two values over the time. So however, at this node point, that means at x equal to say lambda by 2, then 2 into lambda by 2, then 3 into lambda by 2, these are the points where the amplitude will always be 0. That is, irrespective of the time, this point will always be, the amplitude of this point will always be 0. These are the points where it happens, because at that point the sine value will go to 0. So similarly, ER will have maximum value at all x points when the cos omega t will be plus minus 1. So for a fixed x, if I want to find out, as I mentioned, what is the value of the amplitude, then when cos omega t is plus minus 1, these points will get the maximum amplitude. So, omega t cos omega t plus minus 1 means omega t will be m pi, or t will be m pi, and that is omega is 2 pi divided by t, and this is 2 pi divided by t multiplied by t. So, that is the value. So, t will be m multiplied by t by 2. These are the times. If we know the frequency of this omega, then I can find out what is the time period, and from that time period we can find out the time at which this goes to a maximum value. For example, it happens at 0, then t by 2, then 2 of t by 2. These are the times. Then 3 multiplied by t by 2. It is simply the integer multiple of t by 2 at which it will going to have the maximum frequency. So, with this note, I would like to conclude my today's class because I don't have much time. So, in the next class, what we do is we now have the concept of propagating wave, the concept of the superposition of two waves, how these two propagating wave is how this two propagating wave is interfering and forming a standing wave, but all we have for a fixed frequency. Now, next in the next class we try to understand if the frequency is slightly different, then if in that case two waves are superimposing to each other, then what will be the resultant wave. That means so far we are deal with two waves having same frequency, but in the next class what we do, that we superimpose two waves with slightly different frequency and check that what happened if these two waves are superimposed, what should be the nature of the resultant wave. So, with this note I like to conclude here. Thank you very much for your attention. See you in the next class.